morning, good afternoon, and good evening to everyone who joins us from around the world. We're so glad you're here. This is Andrew and Renee. Welcome to the Stack series. Today we are exploring the mathematics of systemic survival.
And I'm just so excited to get into this one. It's truly fascinating.
It really is because, if you ask someone what a dying forest, the physical fiber optic cables of the global internet, and the 2008 financial crash all have in common, they're probably going to look at you like you're crazy.
Right, yeah. On the surface, absolutely nothing.
Exactly. A forester, a network engineer, and a Wall Street banker, they literally speak completely different languages. But, and this is what our analysis today is all about for you listening, if you strip away the bark and the silicon and the dollar bills, and you just look at the invisible scaffolding holding them all together.
You find the exact same mathematical architecture.
Yes, it's wild.
It is. It's this hidden geometry that essentially dictates whether a system lives or dies. And, for a long time, our approach to diagnosing whether one of these massive systems was healthy or sick, it relied on a very mechanical mindset.
Like a car engine, right.
Exactly like a car engine. We treated the global economy or an ancient ecosystem like a machine. If something sounds wrong, you just open the hood, you find the broken belt, you replace it.
And the machine works again.
Right. We expected a very clear binary diagnosis. It's either broken or it isn't.
But when you step into the world of complex, deeply interconnected systems, that mechanical approach just completely falls apart.
It's useless.
Yeah, you can't just take an X-ray of the global supply chain. When a system spans millions of nodes and billions of connections, the diagnostic landscape becomes incredibly murky for everyone involved. A tiny disruption, something that shouldn't matter at all, can sometimes just be absorbed without a ripple.
Yeah, nobody even notices it.
Right. But other times, that exact same tiny disruption shatters the entire system overnight.
Which is really why this journey we're on today is so crucial for anyone trying to navigate the modern world. We are synthesizing a massive stack of cutting-edge research for you. We are pulling from statistical physics, percolation theory, ecology, financial mathematics.
The whole 9 yards.
The whole thing. Because our mission today is to map this hidden mathematical architecture of survival. We need to understand the fundamental laws that govern why some structures endure absolute chaos, while others just collapse under their own weight.
So we're going to take you from the baseline rules of network resilience all the way into this mind-bending, counterintuitive concept called antifragility.
Yeah, that part is going to really change how you see the world.
It totally will. But to do that, we have to start with the foundations, right? What we think we know. We have to clear up some language first, because in our everyday lives, we just throw around words like robustness and resilience as if they mean the exact same thing.
Oh, constantly. People use them interchangeably all the time.
Right. Like a resilient company is a robust company, obviously. But in the fields of ecology and physics, these terms have intensely strict, mathematically distinct definitions.
They're not the same thing at all.
No, and confusing them is actually creating massive blind spots in how we design our institutions, our cities, and, frankly, our own lives.
It's a critical distinction. And to establish this baseline, we really have to look to the foundational work of ecological researchers, like C.S. Halling.
Right. Halling's work is essential here.
Yeah, because Halling wanted a way to mathematically describe how ecosystems respond to trauma. So to visualize his definitions for you listening, imagine a three-dimensional landscape made of hills and valleys.
Okay, so picture a topographical map. You have high peaks, steep ridges, and deep, bowl-shaped valleys. And resting somewhere in one of those valleys is a ball.
Just a standard rubber bell.
Right. And for you listening, that ball represents whatever system you care about. It could be your local town's economy, it could be a coral reef, or even your own immune system. The specific valley the ball is resting in represents the system's current state of equilibrium.
It's the normal day-to-day baseline. Everything is fine.
Exactly. Now, a storm rolls in, a hurricane hits the reef, or maybe a sudden tariff shocks the local economy. In our mathematical landscape, that storm is a physical force pushing the ball up the side of the valley.
And this is where Halling's definition of resilience comes into play.
Yeah.
A highly resilient system is a ball sitting at the very bottom of a deep, steep-sided valley.
Very steep.
Right. So when the storm pushes the ball up that incline, gravity immediately fights back. The moment the storm passes, the ball rolls rapidly down the steep slope right back to the bottom.
It snaps back into place.
Exactly. So resilience, mathematically speaking, is just the speed and efficiency with which a system returns to its original steady state after being displaced.
It bounces back.
It bounces back.
But what if the system isn't in a deep, steep valley? Like, what if the valley is incredibly shallow, almost flat, like a wide basin?
Well, that is a system with very low resilience. Because you apply the exact same amount of force, the same storm, the same economic shock, and the ball rolls much further away from its center point.
Right, because there's no steep wall stopping it.
Yeah, because the slope is so gentle, there's very little gravitational pull bringing it back. So it lingers out there on the edge for a really long time.
And because it's lingering on the edge, it's vulnerable.
Highly vulnerable.
Right, because if a second, even smaller storm hits while it's still trying to recover, it might push the ball over the ridge entirely, and then it drops down the other side of the mountain and lands in a completely different valley.
And that right there is what ecologists and physicists call a critical transition, or a catastrophic regime shift.
It's a point of no return.
Exactly. The ball is now trapped in a new equilibrium, and it is almost always a highly degraded one. So the coral reef becomes a dead zone just covered in algae. The thriving town becomes a ghost town. The original system is entirely lost.
Wow.
So resilience is all about the shape of the valley and the ability to roll back to the center.
Okay, so that's resilience. Now, contrast that, bouncing back, with robustness, because robustness doesn't care about the shape of the valley at all.
Not even a little bit.
Mm-mm.
Robustness is the ability of a system to absorb a disturbance without changing its state in the first place.
Okay.
So if resilience is a rubber ball rolling up a hill and back down, robustness is like a massive block of solid iron sitting in the valley. The storm hits, the wind howls, and the iron block simply does not move.
It just sits there.
It resists the perturbation entirely.
Okay, so resilience is the speed of recovery, and robustness is the capacity to resist being moved at all. That makes perfect sense for, a solid object or an abstract concept like a valley. But the systems that actually govern our lives, right? The internet, the banking sector, global logistics, they're not solid blocks of iron.
No, they're definitely not.
They're massive webs of interconnected pieces. So how do these concepts apply when the system is a vast network?
Well, that requires us to shift our perspective. We have to move from the geometry of landscapes to the topology of networks.
Topology.
Yeah, specifically looking through the lens of a really fascinating area of statistical physics called percolation theory. Now, network topology is simply the study of how individual parts of the nodes are wired together by links.
Okay.
And to understand how these wired structures withstand damage, physicists use a mathematical model called inverse percolation.
Inverse percolation. Okay, I love this visualization from the sources. So for you listening, think of a massive, infinite checkerboard spreading out in all directions. On every single intersection where the lines cross, you place a pebble.
Right.
And the pebbles are your nodes. So maybe they represent internet routers or individual banks or power substations. And the lines drawn between the pebbles are the links. So the fiber optic cables, the financial loans, the transmission wires, you basically have this perfectly connected grid.
Right. And in a fully connected grid like that, information or money or electricity can travel from any one pebble to any other pebble by just following the lines.
It's all connected.
Exactly. This massive unbroken cluster of connectivity is what mathematicians call the giant connected component, or the GCC. As long as the GCC exists, your system is functional. The internet works.
But inverse percolation is about destroying the network, right? It simulates random failure.
Yes. So imagine you close your eyes, you reach out, and you randomly remove a pebble from the board.
Okay, a server goes offline due to a power outage.
Right. Then you reach out again and remove another pebble. A bank loses liquidity and freezes its lending. The fundamental question of percolation theory is, how many pebbles can you remove before the network just stops functioning? At what exact mathematical point does the giant checkerboard fall apart?
Now, you would naturally assume, right, that it's a slow, gradual degradation. You remove 10% of the nodes, the network gets 10% slower. You remove 50%, it operates at half capacity.
It feels like it should be a smooth, concave slope down into failure.
Exactly.
But that is the intuitive assumption, and it is mathematically completely wrong.
Really?
Yeah, and this is the terrifying reality of complex networks. They do not degrade smoothly. They undergo what physics calls a phase transition.
Oh, like water turning into ice?
Precisely the same mechanism. It's not sort of ice and sort of water. It snaps from a liquid to a solid at exactly 32 degrees Fahrenheit.
Right.
As you remove pebble after pebble, the giant connected component just routes the traffic around the missing pieces. The network appears totally fine from the outside.
You wouldn't even know it was breaking.
Exactly. But underneath, the structural integrity is hollowing out. And eventually you hit a mathematically precise critical fraction of nodes, the tipping point.
The edge of the cliff.
Yeah. If you remove just one single pebble past that critical threshold, the phase transition triggers. The entire giant connected component suddenly shatters. In an instant, your massive grid dissolves into millions of tiny, disconnected, useless islands. The network collapses entirely.
Wow. So if the collapse is an invisible cliff edge, the most important question for you and me, since we live our entire lives dependent on these networks, is what determines where that cliff edge is? Is it the same for every network?
It is absolutely not the same for every network. And this is where the underlying math becomes incredibly predictive. The location of that tipping point is governed by a mathematical rule known as the Malloy-Reed criteria.
Okay, let's unpack the Malloy-Reed criteria, but let's try to do it without getting lost in deep algebra.
Good call.
The core concept here is about how the links are distributed among the pebbles, right?
Yes. The survival of the network under random attack depends fundamentally on its degree distribution. In network science, a node's degree is simply the number of connections it has to other nodes. How many handshakes is it making?
Right.
The Malloy-Reed criteria proves that the stability of the giant connected component depends on the ratio between the first and second moments of that degree distribution.
Okay, let's translate those moments into plain English for the listener. The first moment is just the average. So if you count up all the links and divide by the number of nodes, you get the average number of connections per node.
Simple enough.
But the second moment is the variance. It measures how wildly the individual nodes deviate from that average. Does everyone have roughly the same number of connections, or do a few nodes hoard all the connections while everyone else has almost none?
And that variance changes everything. The sources we're analyzing break this down by looking at the two primary types of networks that exist in the real world: random networks and scale-free networks.
Okay, let's look at the random network first. This follows what statisticians call a Poisson distribution. In a random network, most nodes have roughly the exact same number of connections, so the variance is very low.
Yeah, think of a national highway system.
Right.
If you look at most major highway intersections or exit ramps, they connect to roughly the same number of other rows, maybe 3 or 4 directions. You don't have a single intersection in the middle of Kansas that connects directly to 10,000 different roads.
Yeah.
There's a clear, bounded average degree of connectivity.
Right, and because of that even distribution, a random network has a very predictable, somewhat early tipping point when subjected to inverse percolation. If you start randomly removing intersections, eventually you just thin out the roads enough that the East Coast can't reach the West Coast.
Exactly.
But then we have scale-free networks, and these are the ones that truly shaped the modern era.
Yeah. Scale-free networks follow a power law distribution. They're ubiquitous. The physical router structure of the internet is a scale-free network. The web of human sexual contacts spreading a virus is a scale-free network. The global aviation system is a scale-free network.
They're everywhere.
Everywhere. And the defining characteristic of a power law distribution is extreme variance. You do not have an average node.
Right. Instead, you have a massive, almost uncountable number of tiny nodes that only have 1 or 2 connections. And then you have a very, very small number of gigantic hubs that possess millions of connections.
And this structural difference leads to a profound paradox. It was famously detailed in the early 2000s by statistical physicists like Reuven Cohen, Shlomo Havlin, and Albert Laszlo Barabasi. They discovered what is essentially the Achilles heel of modern civilization.
The Achilles heel.
Yeah. They took the physical structural map of the internet, which is a textbook scale-free network, and they subjected it to inverse percolation. They wrote an algorithm to simulate nodes randomly failing.
So they started virtually deleting routers and servers just to see when the internet would shatter.
And what they found initially looked like a miracle. A scale-free network is unbelievably, almost impossibly robust to random failures because the vast, overwhelming majority of the nodes are those tiny one-connection offshoots. A random failure is statistically guaranteed to hit an unimportant node.
That makes sense.
If you blindly throw a dart at a map of the internet, you are going to hit somebody's home Wi-Fi router, not a massive regional data center.
Right, because there are billions of home routers and only a few major data centers.
Exactly. So Cohen and his team found that you can randomly wipe out up to 99% of the nodes in a scale-free network. And the giant connected component still survives. The internet routes around the damage and stays online.
I mean, that sounds like an incredible piece of engineering. It sounds like we built the ultimate robust system.
It does, until you look at the dark side of the paradox.
Oh.
Yeah. The exact same mathematical variance that makes scale-free networks immune to random failure makes them terrifyingly fragile to targeted attacks.
Ah. Because if a bad actor or, a highly evolved pathogen doesn't act randomly, but instead specifically seeks out and attacks the most highly connected nodes, the math reverses completely.
Completely reverses.
Huh?
The researchers proved that if you stop acting randomly and instead deliberately take out just the top 3% of the most highly connected hubs, you will completely and utterly destroy the giant connected component. The phase transition happens almost immediately. The network shatters.
So just to really visualize this power law of vulnerability for you guys listening, think about the airline system. The aviation network operates on a hub-and-spoke model.
Yeah.
If a massive blizzard hits a tiny regional airport in Idaho and shuts it down, it represents a random failure of a low-degree node. It does absolutely nothing to the global flight map. Planes keep flying everywhere else. But imagine a malicious attack that simultaneously shuts down O'Hare in Chicago, JFK in New York, and Heathrow in London on the exact same morning.
You haven't just inconvenienced a few travelers. You have severed the critical hubs that hold the disparate regions of the globe together.
The whole thing falls apart.
Yeah, the giant connected component of international aviation fragments instantly into isolated local clusters.
So the hubs are the ultimate source of strength, but they are also the fatal weakness. But let me just push back on this framework for a second.
Sure.
If we have the mathematical models and we know exactly where the vulnerabilities are, like we know what the top 3% of hubs are, doesn't that mean true resilience is actually incredibly simple to achieve?
How so?
Well, isn't the solution just to identify those hubs, build massive, impenetrable fortresses around them, and protect them with everything we have? Why doesn't that just solve the problem of systemic survival right there?
That is a brilliant pushback. And it actually represents the exact pivot point where modern complex system science begins to violently disagree with classical engineering.
Okay, why?
Because you are suggesting a static defense mechanism. Building a fortress around a hub assumes that the threat is simple physical removal and that the environment is predictable. But the real world is not a sterile mathematical checkerboard. The real world is incredibly dynamic, constantly shifting, full of noise, variability, and completely unforeseen stressors.
Which brings us perfectly to the second phase of our exploration, the active debate currently raging in the scientific community, where science disagrees. Because science is currently questioning whether simply bouncing back to where you were resilience or stubbornly resisting change robustness is actually the optimal survival strategy in a chaotic universe.
Right, because if you just bounce back to your original state after a shock, you haven't adapted. You haven't learned anything from the trauma.
Exactly. And this profound limitation of both resilience and robustness introduces a revolutionary mathematical concept developed by the scholar and former options trader Nassim Nicholas Taleb. It is the concept of antifragility.
Yes, antifragility. It's brilliant.
Taleb makes a simple but mathematically rigorous argument. The opposite of fragile is not robust.
Now, for most people, that sounds like a contradiction.
It really does. I mean, if a crystal glass drops on the floor and shatters, it's fragile. If a plastic cup drops and doesn't break, we say it's strong, it survived. So isn't strong the opposite of fragile?
Not if you map it mathematically.
Right.
Taleb asks us to look at a spectrum of how a system responds to variability, stress, and time. Let's define the 3 points on this spectrum. On the far left, you have fragility. A fragile system is mathematically defined as a system that is fundamentally damaged by variability, randomness, and stress. The more volatility you introduce, the more it degrades and eventually breaks.
Makes sense.
No.
And in the middle of the spectrum, you have robustness. As we defined earlier with the iron block, a robust system simply ignores variability. It doesn't break when stressed, but it also doesn't change. It remains exactly the same.
Right, so if fragility is a negative response to stress and robustness is a neutral, zero response to stress, what is the mathematical opposite of negative?
It must be strictly positive.
Exactly. Therefore, the true opposite of a fragile system is not one that resists stress, but one that actively benefits from variability, stress, and noise. An antifragile system requires disorder to improve its functionality. It uses the shock as fuel to grow stronger.
But how does that actually work at a structural level? I mean, how can a system possibly mathematically benefit from chaos and damage?
It all comes down to the geometry of the system's response to the stressor. Specifically, we have to look at whether the system's payoff function is concave or convex. This geometry is rooted in a fundamental, deeply powerful theorem of probability known as Jensen's inequality.
Okay, Jensen's inequality sounds like really heavy textbook material. Let's try to avoid the Greek letters and just focus on the shape of the curve. What does this mean conceptually?
Imagine drawing a graph. The horizontal axis running left to right represents the intensity of a random event, the stressor.
Okay.
The vertical axis going up and down represents the payoff or the overall health of the system.
Okay, I have the graph in my head.
If a system is fragile, its response curve bows downward. It looks like a frown. This is a concave curve. A concave response means that as the stress gets slightly bigger, the damage to the system accelerates and gets exponentially worse.
So for you listening, think about jumping off a wall. If you jump off a 1-foot wall 10 separate times, you absorb a total of 10 feet of impact over time, and your legs are perfectly fine.
Right, totally fine.
But if you jump off a 10-foot wall just one single time, your legs shatter. The total distance is the same, but the damage from the stressor accelerates exponentially faster than the height of the wall. That accelerating damage is the hallmark of a concave, fragile response.
Exactly. The downside risk in a concave system is completely uncapped and accelerates toward ruin. Now, an antifragile system has the exact opposite geometry. Its curve bows upward, it looks like a smile. This is a convex curve.
A convex curve.
Yeah, a convex response means that as the stress increases, the benefit or payoff to the system increases exponentially, while the potential downside or damage is strictly capped at a known minimum.
So the worst case scenario is a small, manageable loss, but the best case scenario is an exponentially massive gain.
Yes. And Jensen's inequality reveals a profound mathematical truth about these curves. If your system's response to stress is convex, the expected mathematical return of experiencing extreme, highly variable volatility is actually much higher than the return of experiencing safe, average, uniform conditions.
Wait, let me make sure I'm hearing this right. The math actually proves that exposing yourself to extreme, chaotic volatility is safer and more profitable than being carefully average, as long as your system is convex.
Yes, because in a convex system, the occasional extreme positive event produces a payoff that vastly outweighs all the small cap negative events combined. If you try to smooth out the environment and stay in the average middle, you eliminate the volatility that your system requires to generate those massive nonlinear gains.
Wow. And this logic gives birth to what Taleb calls the barbell strategy for risk management and survival.
I love this concept.
It's so good. Imagine a physical weightlifting barbell. You have heavy weights loaded on the two extreme ends and absolutely nothing on the long bar in the middle.
The barbell strategy demands that you divide your exposure. You combine extreme risk aversion on one side with extreme risk-taking on the other side, while completely avoiding that fragile middle.
So if you apply this to finance, right, it means you don't put 100% of your retirement in a moderate risk mutual fund.
No, definitely not.
Because that fund sits in the fragile middle. It yields average returns, but is totally exposed to being wiped out by an unpredictable black swan market crash. Instead, you build a barbell. You put 90% of your wealth into ultra-safe, inflation-protected government treasury bonds. You lock in your survival.
You cap your downside.
Exactly. Then you take the remaining 10% and put it into the most highly volatile, extremely risky venture capital bets you can possibly find.
Because the downside of the venture capital is strictly capped. You can only lose that 10% and nothing more. But the upside is highly convex. One of those wild bets might return 10,000%. You've engineered a system that is immune to total ruin on one end, but actively harvests the chaotic volatility of the universe on the other.
Let's bring this down to biology, because your own body is actually the ultimate example of an anti-fragile system. I mean, think about going to the gym and lifting weights. When you lift a heavy dumbbell, you are not protecting your muscles. You are actively introducing acute volatility, physical stress, and literal micro tears into the muscle fibers. You are causing structural damage.
Right. But the biological system has a convex response to that specific type of localized stress. During the recovery period, the body doesn't just repair the muscle back to its original state. That would be mere resilience.
Right, bouncing back.
Yeah, but the body overcompensates. It builds the muscle tissue back thicker, denser, and stronger than it was before the stress was applied. The system literally consumes the damage as fuel for growth.
But if you try to live in the fragile middle, like if you decide that any stress is bad, so you just lay in bed all day and experience zero physical volatility, your muscles atrophy. They degrade.
You're harming them by protecting them.
By protecting them completely, you guarantee their weakness. So the barbell strategy for physical health is periods of intense, heavy lifting, followed by periods of absolute restorative rest. Extreme ends, nothing in the middle.
And this biological reality is currently revolutionizing medical mathematics, which brings us to the recent, highly impactful work of researchers like Eduardo Sontag from the Sontag Lab.
Sontag's work is fascinating.
It really is. Sontag recently published a paper translating this exact concept of convex antifragility into the realm of dynamical systems, specifically looking at how we treat life-threatening diseases.
He's applying the math of stock market volatility to oncology.
Yes, he is using it to model tumor growth and infectious diseases. Sontag defines antifragility in a biological system by analyzing something he calls the logarithmic rate of the system.
The logarithmic rate.
Yeah, which is just a mathematical way of tracking how fast a population of cell, like a tumor, is growing or dying relative to a specific parameter, like the dose of a drug.
So we map the tumor's response to chemotherapy.
Exactly. And let's look at this through the lens of Jensen's inequality. We introduce a drug, and we map the logarithmic rate of the tumor's survival. In many cases, the researchers find that the tumor's response to the toxicity of the drug is a strongly convex function.
Meaning the curve smiles.
Right. This means that at very low doses, the drug barely slows the tumor down at all. But as you increase the dose to highly toxic levels, the rate of tumor death accelerates exponentially. The curve smiles upward in favor of the medicine.
So if the tumor's death curve is convex, what does Sontag's math tell us about how doctors normally prescribe medicine? Because usually if you get sick, the doctor gives you a pill to take once a day, every day, right? A constant average dose.
Sontag's math mathematically proves that if the system is convex, a constant average daily dose is the absolute worst possible strategy.
Wait, really? Why?
Because that average dose sits right in the fragile middle of the barbell. An average steady dose provides a moderate amount of toxicity, which isn't enough to leverage the exponential killing power of the convex curve. Instead, it just subjects the tumor to a mild, constant pressure, and biological systems are adaptive.
Oh, I see where this is going.
Yeah, that constant average pressure actually acts as a training mechanism, allowing the tumor cells to mutate, adapt, and develop resistance to the drug.
So by trying to be steady and average, you are actually training the cancer to become invincible.
Exactly.
What is the mathematical alternative then?
The alternative is applying the barbell strategy to chemotherapy. The math dictates that you must use pulsed therapies. You design an extreme treatment protocol. First, you hit the patient with an incredibly high, violently toxic dose of the drug,
Okay.
pushing the intervention far to the right side of the convex curve to maximize the exponential destruction of the tumor cells.
But that dose is highly toxic to the patient too, isn't it?
It is, which is why the second half of the barbell is just as important. After the extreme pulse, you immediately drop the dose to absolute zero, no medicine at all.
Wow.
This allows the healthy, non-cancerous tissue, which often recovers faster than the mutated cells, to rest and regenerate. You alternate back and forth between maximum extreme toxicity and maximum extreme rest. You are actively leveraging the mathematical anti-fragility of the dynamic system to eradicate the disease.
Yeah.
You are weaponizing volatility.
It's incredible. I mean, we are literally learning that avoiding extremes is what kills us. But wait, I have a massive pushback here.
Okay, let's hear it.
The theory of anti-fragility sounds flawless on paper. A barbell strategy works for an investor's portfolio, pulsing extreme chemo works for tumors, and weightlifting works for muscles.
But there has to be a physical limit to convexity, right?
What do you mean? Like, if I go to the gym and drop a 500-pound barbell directly onto my chest, my system doesn't overcompensate. My ribs shatter, my lungs puncture, and my system dies. How do you mathematically know when a system is about to cross the invisible line from benefiting from stress to experiencing a catastrophic critical transition? How do we measure the breaking point of the giant connected component before it shatters?
That is the ultimate million-dollar question.
Yeah.
And it transitions us beautifully into our third area of exploration, the frontiers of this science. What might change everything?
Right.
Because you're entirely correct. Antifragility is bounded. Every system has a breaking point. And to know when variability turns fatal, we cannot just look at the static structure of the network hubs, and we cannot just trust the convexity of the payoff curve. We have to look at the invisible information the system is constantly radiating as it struggles to maintain its balance. We have to measure the warning signals of impending collapse.
So we're talking about predicting a phase transition before the network shatters. But how do you measure a signal from a system that looks perfectly fine on the outside?
The cutting-edge tool for this endeavor comes from the world of information theory. It is a mathematical metric called Fisher information, often abbreviated as FI.
Fisher information.
Yeah. Now, when most people hear the word information, they think of data storage, like how many gigabytes are on a hard drive or the text in an email. But in the context of dynamic physical systems, Fisher information means something entirely different.
It's not about data volume at all.
No. Fisher information is a measure of dynamic order. It measures the predictability, the stability, and the quality of measurements you could extract from a moving system. It essentially calculates how tightly organized and coherent a system's internal behavior is at any given moment.
So how do we read this metric? What are the rules for translating Fisher information into a warning system?
There are three fundamental rules you need to understand to read the health of a system using FI. First, if you measure a system and it exhibits persistently high Fisher information, it means there is very low variability in its behavior. The system is operating in a highly stable, tightly organized, orderly regime. You can easily and accurately predict what it will do 1 second from now.
High FI equals stability. Got it.
Second, if you track the system over time and you observe a slowly decreasing trend in its Fisher information, that is your early warning signal. A dropping FI means the system is slowly losing its internal structural organization. Its functionality is degrading, and importantly, its internal variability is starting to spike. The noise is increasing.
The parts of the system are losing synchronization, starting to wobble.
Exactly. It's wobbling. And the third rule is the most critical. The sharp, sudden plummet in Fisher information is the ultimate red flag. When FI drops off a cliff, it mathematically indicates that an impending catastrophic regime shift is about to occur.
The critical transition.
Yes. It means the system has exhausted its ability to absorb stress, and it is about to flip over that ridge we talked about earlier and fall into a completely different, often degraded valley.
Think about driving a car down the highway at 70 miles an hour. When you are operating with high Fisher information, your steering wheel is perfectly smooth under your hands. The tires are gripping the asphalt, the alignment is perfect, and the car is responding exactly as you intend. You are in a highly ordered, highly predictable regime.
Right.
But let's say one of your front tires starts to severely lose its tread, or maybe a bolt in the suspension comes loose.
The physical structure of the car is degrading.
Right. And how do you perceive that degradation? The steering wheel starts vibrating violently in your hands. The car pulls unpredictably to the left and right. The variability of your drive is spiking. That vibration is a physical manifestation of slowly decreasing Fisher information.
That's a great way to put it.
Because the vibration doesn't mean you have crashed yet. The car is technically still moving forward on the road. The system hasn't shattered. But that dropping Fisher information is an urgent, early warning signal from the physics of the vehicle that you are losing structural order. If you ignore that vibration and don't slow down, a catastrophic regime shift, a high-speed blowout that sends you off the road, is mathematically imminent.
That is a phenomenal conceptualization. The violent vibration is the loss of Fisher information. And what is incredible is that researchers are now seeing this exact same vibration across entirely different scientific disciplines. We see it in natural ecosystems constantly. Ecologists like Cabezas and Mayer have successfully utilized Fisher information as a diagnostic tool for aquatic ecosystems.
Applying information theory to a lake.
Yes. Imagine a pristine, clear, highly oxygenated lake, what ecologists call an oligotrophic ecosystem. It is healthy, stable, and has high Fisher information. But over the years, agricultural runoff from nearby farms introduces massive amounts of phosphorus into the water. For a long time, the lake looks completely fine to the naked eye. The water is still clear. The fish are swimming.
The giant connected component is routing around the damage.
Exactly. But mathematically, under the surface, the lake's Fisher information starts a slow, terminal decline. The populations of microorganisms and chemical balances start vibrating wildly, swinging through massive localized booms and busts. The system is wobbling. Then suddenly, the FI metric plummets. Within days, the lake flips. It undergoes a regime shift and becomes eutrophic.
It turns into a murky, dead zone, completely choked by toxic algae, where nothing else can survive.
Yeah. And the key here is that if they were tracking the Fisher information, they could have seen the mathematical vibration and predicted the algae bloom long before the lake actually died. They could have intervened.
They absolutely could have. And researchers are also using this exact same math to track the adaptive cycles of forests after massive wildfires, right?
They are. By measuring the Fisher information of the new growth, they can mathematically chart how the ecosystem is slowly reorganizing itself out of the chaos, regaining its internal order, and restabilizing into a new equilibrium.
And it's not just limited to ecology. The sources highlight that this math was actively deployed during recent global health crises.
Yes, the applications of information theory are expanding rapidly into human epidemiology. During the SARS-CoV-2 pandemic, researchers utilized a complex analytical tool known as the Shannon-Fisher causality plane. This allowed them to track the infection dynamics across 15 different countries simultaneously.
Okay, what exactly is a causality plane?
In simple terms, it's a two-dimensional graph that maps out the relationship between entropy, which is a measure of pure randomness and chaos, and Fisher information, our measure of dynamic order. The researchers took the daily infection data from these countries, but they didn't just look at the raw case numbers. They analyzed the numbers to extract the underlying information of the disease spread. They ranked the countries based on how organized or chaotic their systemic response was.
So they were mathematically charting which countries were in control and which were losing their grip.
Exactly. And the data revealed a stark mathematical divide. Countries that were highly proactive nations that implemented immediate, aggressive testing, strict quarantines, and rapid social distancing protocols maintained their position in a region of the causality plane defined by low entropy and high reliability.
They kept their steering wheel smooth. They maintained high Fisher information.
Yes. Despite the presence of the virus, their societal system remained highly ordered and predictable. The interventions kept the system from wobbling. Conversely, the reactive countries, those that hesitated, delayed policy implementation and waited until the disease was already rampant in the population, showed a completely different trajectory. On the causality plane, you could watch their data points plummet in real time. Their Fisher information collapsed, and their entropy skyrocketed.
Wow.
They descended rapidly into the chaotic region of the graph, mathematically indicating a complete and total loss of systemic control over the pathogen spread.
Okay, but this brings up a massive conceptual collision. Earlier, when we were discussing Nassim Taleb and the barbell strategy, we established that a perfectly stable system, one that avoids all stress and variability, is actually fragile. It rusts. It atrophies. We said we need volatility to be antifragile. But now we are saying that high Fisher information, which literally means very low variability and high stability, is the definition of a healthy system. So if high Fisher information means zero variability, isn't a high FI system secretly incredibly fragile? How do these two scientific truths coexist?
That is one of the most profound observations we can make, and you have just accurately identified the paradox of variability. Reconciling this paradox is currently one of the most fascinating frontiers in complex systems research, specifically spearheaded by scientists studying physiological networks.
Okay.
The answer to the paradox is that a healthy system requires both extreme stability and wild chaos, but it segregates them into different layers of the architecture.
Explain that layering. How can a system be both stable and chaotic at the exact same time?
For a vital core system to remain perfectly stable and highly ordered, meaning it maintains that crucial high Fisher information and tight homeostasis, it mathematically requires the existence of a secondary subordinate system whose entire purpose is to absorb the chaos of the outside world.
Let's ground this in a biological example so we can really see it working.
Let's look at human blood pressure. Your blood pressure is a vital life or death metric. It needs to be incredibly stable to keep your organs functioning. Statistically, a healthy blood pressure needs to map tightly to a very narrow, predictable Gaussian bell curve.
Right. If your blood pressure deviates too far from that narrow center, you suffer a stroke or heart attack. You die.
Exactly. Your blood pressure must be a strictly homeostatic, highly stable variable.
But the world you live in is not stable. You go from sleeping in a bed to suddenly standing up, to running to catch a bus, to getting terrified by a loud noise. You are constantly subjected to severe, unpredictable physical and emotional shocks. So how does the vital blood pressure stay perfectly smoothly Gaussian while the universe is throwing chaotic stressors at the body?
Because a secondary system steps in to take the hit. In your circulatory system, that secondary absorbing variable is your heart rate. If you measure a healthy person's heart rate over time, it does not follow a neat, tight Gaussian bell curve at all. Instead, it has a highly erratic, right-skewed, wildly variable statistical distribution.
The heart rate is the shock absorber.
Exactly. When you stand up suddenly, gravity tries to drop your blood pressure. Instantly, your heart rate spikes wildly, beating frantically faster to counteract the gravitational pull. It absorbs the shock of the environmental change so that the pressure inside the vessels can remain perfectly smooth and stable. True biological health is defined by this exact architectural relationship, having a rigid, deeply protected homeostatic variable that is surrounded and defended by a wildly fluctuating, chaotic absorbing variable.
So the heart rate provides the antifragile volatility, allowing the blood pressure to maintain its high Fisher information.
Yes, and the proof of this dynamic comes from studying what happens when people get sick. When researchers study patients with severe chronic diseases like advanced diabetes or severe heart failure, they find that this statistical relationship actually inverts.
The layers flip.
The layers fail. In a severely diseased patient, the heart rate loses its ability to fluctuate. It becomes rigid, predictable, and Gaussian. It loses its absorbing capacity. And because the shock absorber is broken, all the environmental stress transfers directly to the vital system. The patient's blood pressure becomes highly skewed, erratic, and wildly variable. The shock hits the vital core, the Fisher information plummets, and the organism is in severe critical danger.
So going back to the car analogy, the vibration in the steering wheel isn't inherently a bad thing as long as it is the suspension and the shock absorbers doing the vibrating to absorb the potholes. But if the shock absorbers freeze up, the force of the pothole transfers directly into the steering column and the car tears itself apart.
That is exactly the mechanics of the paradox of variability. You must have structural flexibility on the perimeter to maintain order at the core.
This math is brilliant for understanding natural ecosystems, human physiology, and viral pandemics. Nature has had billions of years to evolve these deeply layered, mathematically elegant shock absorbers. But this brings me to a deeply troubling question.
Oh.
Human beings don't rely solely on natural systems anymore. We build completely artificial, intentionally engineered, highly optimized networks to run our civilization. I'm thinking about the global supply chain, international banking, the stock market. Do these exact same mathematical laws of scale-free vulnerability, convex antifragility, and critical phase transitions apply to our engineered money and our shipping routes? Or have we somehow, through modern engineering, managed to design our way out of the laws of physics?
We absolutely have not engineered our way out of the laws of physics. In fact, the tragic irony is that by largely ignoring these mathematical laws in our pursuit of profit, we have engineered synthetic systems that are uniquely poised for catastrophic, sudden collapse.
And that brings us to the final and perhaps most urgent section of our exploration: the implications for our economics, our ethics, and our society at large. Because when we apply the math of nature to the networks of human finance, a very terrifying picture emerges.
It really does. As we just discussed, nature survives by building in redundancy, localized boundaries, and wild absorbing variables to dampen shocks. But in modern finance and global logistics, our relentless, unyielding pursuit of absolute efficiency has systematically eradicated those natural defenses.
We view redundancy as wasted money.
Yes. We view absorbing variables as friction. We have intentionally stripped the shock absorbers out of our societal vehicles.
Which brings us directly to the defining economic event of our generation, the 2007 to 2009 global financial crisis. The narrative we're usually sold is that the crash was caused by greedy bankers writing bad subprime mortgages. And while that's true, it's only looking at the individual pebbles.
Right.
The subprime mortgages were just the match. The explosive fuel that almost burned down the global economy was a fundamental failure to understand network theory.
Exactly. Leading up to the 2008 crisis, the prevailing dogma in macroeconomic theory was deeply flawed. The core belief was that massive diversification and deep, complex interconnectedness inherently and automatically reduced systemic risk.
The mathematical assumption was that if a single bank held a toxic asset, like a bad mortgage, but that bank was intricately connected to 100 other healthy banks through derivatives and loans, the massive network would dilute the risk.
The belief was that the massive giant connected component would act as an infinite shock absorber. The toxicity would just dissipate into the vast ocean of capital.
And for a long time, during periods of low stress, it appeared to work exactly like that. The system seemed incredibly robust.
But researchers like Andrew Haldane, Stefano Battiston, and others eventually mapped the topology of this financial web, and they exposed the two interconnected to fail paradox.
What is the paradox?
They proved mathematically that initially, as you increase connections between banks, high connectivity does act as a shock absorber. It shares the load. But Returning to the concept of phase transitions in percolation theory, there is a strict critical threshold of density.
A tipping point.
Yes. Once the financial network passes a certain level of complex interconnectedness, the underlying mathematics of the system violently invert.
The network behavior flips.
It flips entirely. Past that critical density, the massive web of connections no longer absorbs the shock. Instead, the connections become a frictionless superhighway for financial infection. The network itself becomes the very mechanism that guarantees the contagion spreads to every single node.
Think about a team of climbers scaling a steep, treacherous mountain face. To ensure everyone's safety, they tie themselves together with a long, heavy rope. The logic is sound. If one climber loses their footing and slips, the rope catches them. The collective weight and friction of the rest of the network absorb the shock of the single failure. That is the intended benefit of interconnectedness. The rope is the shock absorber. But imagine if they tied too many people to the same rope and they're standing on sheet ice. The network is too dense and the environment is highly volatile. Now, if 3 climbers happen to slip at the exact same moment, a correlated shock, the combined kinetic energy of their fall instantly exceeds the friction holding the rest of the team to the ice. The rope no longer saves them. Instead, the rope acts as a conduit for the extreme force, violently ripping the remaining climbers off the mountain.
The safety mechanism transforms into an amplification mechanism. The interconnectedness causes a total system collapse.
Exactly.
And that is a chillingly accurate visualization of the 2008 crash. The derivative contracts were the ropes tying the global banks together on an icy slope. And to understand the exact mathematical physics of how that financial rope pulls everyone off the cliff, complex systems physicists and economists developed an analytical framework known as the debt rank algorithm.
Okay, debt rank. This is where we move away from just looking at the size of a bank's cash reserves, right?
Yes. Debt rank provides the microscopic mathematical foundation for how shock propagation actually operates in a financial network. It does not care about the sheer size of the bank. It cares entirely about the topology of their debts. Who owes exactly how much to whom? The debt rank algorithm works by mathematically iterating the balance sheet identities of individual institutions round by round.
Walk me through a simulation of that algorithm. How does it trace the infection?
It operates on a very simple, relentless rule of accounting. If a borrower takes a financial hit and loses equity, they mathematically transfer a proportional amount of that shock to the lender who holds their debt because the lender's asset is now worth less. The debt rank algorithm traces this single shock as it bounces from node to node across the network.
So Bank A loses $1 billion on bad mortgages. Because of that loss, Bank A cannot fully honor its obligations to Bank B. Bank B now has a hole in its balance sheet, which means Bank B suddenly cannot honor its derivative contracts with Bank C.
And Bank C is forced to mark down its assets, meaning it can't pay Bank D, and the contagion spreads outward in a cascading wave of forced devaluations. But the true genius of the debt rank research, pioneered by scientists like Bardocchia, Battiston, Caccioli, and Caldarelli, is that they didn't just trace the bounces. They cast this entire, incredibly complex dynamic into a single massive matrix equation. They mapped out the global interbank leverage matrix.
A matrix being a massive mathematical grid showing every single loan and dependency between every major bank.
Exactly. And through rigorous mathematical proof, they demonstrated that the ultimate stability of the entire global financial system boils down to one specific property of that massive matrix. It comes down to the matrix's largest eigenvalue.
Okay, you promised me earlier that we wouldn't get completely lost in textbook algebra, but you just dropped largest eigenvalue on me.
I know.
For those of us who haven't taken linear algebra in a decade, what does an eigenvalue actually represent in the real physical world, and what does it mean for the security of the money sitting in our bank accounts?
Think of an eigenvalue conceptually as a multiplier of resonance. Imagine a massive suspension bridge. Every bridge has a natural acoustic resonance. If the wind blows and hits the bridge at just the right frequency, its resonant eigenvalue, the swaying of the bridge doesn't just fade away. The physical structure catches the energy, and the swaying amplifies, growing violently larger with each gust until the steel tears itself apart and the bridge collapses.
Like the famous footage of the Tomaneras Bridge twisting in the wind until it broke.
Exactly. In the context of the interbank leverage matrix, the largest eigenvalue acts as that exact same multiplier of resonance for financial shocks. It mathematically determines whether an economic shock will slowly dampen out or violently amplify until the system shatters. The math is stark, binary, and absolutely ruthless.
Wow.
If the absolute value of the system's largest eigenvalue is less than say, 0.910, the system is fundamentally stable.
Because if the multiplier is zero point 0.9, a $100 shock bounces to the next bank and becomes a $90 shock, then an $81 shock. It shrinks with every iteration. The network absorbs the energy, the climbers hold the rope.
Precisely. The system naturally damps the perturbation. But if the structure of the debts shifts and the largest eigenvalue becomes greater than 1, say 1.1, the entire architecture becomes fundamentally unstable. In that regime, a tiny microscopic microshock, a rounding error in a small subprime mortgage portfolio, will be caught in a vicious, self-feeding feedback loop.
It's just going to grow and grow.
The geometric topology of the network will mathematically multiply that tiny shock by 1.1, then 1.21, then 1.33. Round after round, it amplifies the damage, causing massive equity losses across the grid, eventually triggering an uncontrollable cascade of institutional defaults.
The resonant frequency tears the bridge apart. The rope pulls everyone off the mountain. So this math is terrifyingly elegant, but is it purely theoretical? Did the researchers actually run this debt rank algorithm on real-world banking data?
They did, and the empirical results are staggering. The researchers applied this exact eigenvalue framework to a deeply detailed dataset encompassing 183 publicly traded European Union banks over a 5-year period from 2008 to 2013. They measured what they called the amplification factor of the real-world network.
Yeah.
They ran a simulation where they introduced an incredibly small, seemingly insignificant exogenous shock into the system. They modeled a scenario where the banks suffered a tiny 0.5% devaluation in their external assets.
Half of 1%. I mean,
Yeah.
in the grand scheme of global finance, 0.5% is a rounding error. It's a slightly bad Tuesday on the stock market. It should be entirely harmless.
It absolutely should be harmless. But when they ran the algorithm, they found that even during normal, relatively calm economic times, the complex topology of the EU financial network mathematically amplifies that tiny 0.5% shock by a factor of 3.
It triples it.
The interconnectedness triples the damage before it dampens out.
Tripling a tiny shock is bad, but maybe manageable.
But then they modeled a crisis period. During periods of high systemic stress, when bank leverage increases and liquidity tightens, the largest eigenvalue of the matrix shifts upward. And in that heightened state, they found that the exact same tiny 0.5% microshock is amplified by a massive factor of 6.
6 times.
The internal geometry of the debt network actively multiplies the initial damage 6-fold, purely because of how the links are structured. The network itself has generated the destruction.
Which raises a profound, massive societal question for you, listening right now. Think about how our governments responded to the 2008 crash. Are our regulators actually looking at the right things? After the crisis, global regulators implemented policies forcing individual banks to hold more cash reserves. They stress-tested the individual nodes on the checkerboard.
Right, they looked at the pebble.
But if the math proves that catastrophic risk isn't just about how much cash a single bank holds, but is actually deeply embedded in the topology of its hidden connections, shouldn't we be regulating the shape of the network itself? Shouldn't global central banks be monitoring the largest eigenvalue of the financial system in real time? Exactly the same way ecologists monitor the fissure information of a lake to prevent it from dying.
It is the absolute critical imperative of our time. We are currently trying to regulate hyper-complex, massively intertwined global networks as if they were simple, isolated machines. We obsess over the health of the individual bank or the population of a single species or the supply inventory of a single hospital. We focus on the nodes, completely failing to realize that the true existential threat, mathematical phase transition that will abruptly shatter the giant connected component of our civilization, is hiding in plain sight within the architecture of the links between them.
So what does this all mean? Let's zoom out and synthesize this incredible, sprawling journey we've been on today. We started by looking at a simple ball resting in a valley, and we realized that true survival, whether you're looking at statistical physics, biological ecosystems, or global economics, requires far more than just bouncing back from a shock.
It requires a deep understanding of the structural architecture of our networks. It requires knowing when and how to protect the massive, highly connected hubs that hold our scale-free aviation and internet grids together.
And it requires us to fundamentally rethink our deeply ingrained cultural relationship with stress and volatility. We must learn to utilize the convex mathematics of antifragility. We have to recognize that attempting to protect a system from all noise and variability doesn't make it robust. It slowly starves the system of its adaptive capacity and pushes it into a state of extreme hidden fragility.
We need to intentionally employ the barbell strategy in our investments, our medicine, and our lives, exposing ourselves to small, beneficial, manageable stresses so we can grow structurally stronger, while simultaneously implementing extreme safeguards to protect ourselves from ruinous black swan events.
And finally, we learned that survival is about observation. We must actively monitor the invisible informational warning signals that the dynamic systems around us are constantly broadcasting. We have to learn to look for the subtle drop in Fisher information. We have to feel for the wild spiking vibrations in the steering wheel so we can mathematically predict when an ecosystem, a viral pandemic, or a global financial market is about to cross that invisible critical threshold and suffer a catastrophic regime shift.
We have to ensure that our vital central systems are surrounded by chaotic, flexible absorbing variables designed to take the hits. Because the math is unforgiving. If we don't build those shock absorbers and we don't track those signals, we are flying completely blind. We are living under the deeply dangerous assumption that a system is totally robust right up until the exact microsecond it violently shatters.
Which brings me to a final provocative thought for you to ponder as you go about your day. It's something we haven't explicitly named yet, but it is the haunting logical conclusion that builds on everything we've uncovered. Modern society is completely, utterly obsessed with the concept of efficiency and optimization. We want to smooth out every global supply chain so that parts arrive just in time, with zero costly inventory sitting in warehouses. We standardize our education systems to eliminate variables and remove statistical outliers. We engineer highly uniform, perfectly hedged financial products. We are collectively trying to engineer all the noise, all the friction, and all the chaotic volatility out of the human experience.
We are trying to erase the very thing we need.
Exactly. But if the fundamental laws of mathematical probability dictate that removing all volatility completely eliminates a system's ability to be antifragile, are we accidentally engineering our own global civilization to be maximally fragile to the next inevitable black swan event?
That is the terrifying paradox of modern efficiency. By systematically removing the small, daily, chaotic fluctuations that keep our societal muscles strong, we're unwittingly setting ourselves up for the one massive, systemic earthquake that will break the rigid, brittle structure of our world.
What if we reversed our entire philosophy? What if, instead of constantly optimizing for perfect smoothness and zero friction, we actually designed our institutions to experience small, continuous, chaotic micro-stresses on purpose? What if we built supply chains, banking sectors, and personal lives that didn't just passively hope to survive the X-ray showing a broken bone, but were structurally designed to require the bone to be broken, precisely so it could heal back infinitely stronger? That is the true hidden mathematics of systemic survival. Before we wrap up, thank you to all our partners, sponsors, and scholars who made this podcast and the research possible. We're truly grateful for your support. And to our listeners, thank you for being part of this journey with us. We hope you enjoyed today's discussion. If you did, be sure to subscribe and support us on Patreon. And of course, you can write to us in comments if a specific topic needed to be covered, which help us all to grow. Until next time, stay curious, keep learning, and let the search for wisdom guide you forward. Have a great day.